Lesson: Feature Engineering Concepts for AI Models. Feature engineering is a critical step in the development of AI models, serving as the bridge between raw data and the powerful insights AI can generate. This process involves the creation, transformation, and selection of features that enhance the predictive performance of machine learning algorithms. The importance of feature engineering cannot be overstated, as the quality of features directly affects the model's ability to learn patterns and make accurate predictions. The first step in feature engineering is understanding the data. This involves a thorough exploration of the dataset to identify potential features and understand their characteristics. Professionals typically use tools such as Python's Pandas library for data manipulation and visualization libraries like Matplotlib or Seaborn for initial data exploration. These tools help in understanding the distribution of data, identifying missing values, and detecting outliers, all of which are crucial for developing effective features. Once the data is well understood, the next step is to clean and pre-process it. This stage involves handling missing values, encoding categorical variables, and normalizing numerical features. Missing values can be addressed through methods like mean imputation or using more sophisticated techniques such as k-nearest neighbors imputation. Categorical variables can be encoded using one-hot encoding or ordinal encoding, depending on whether the categories have an inherent order. Normalization techniques such as min-max scaling or z-score standardization are applied to numerical features to ensure they are on a similar scale, which is particularly important for algorithms sensitive to feature scaling like k-nearest neighbors and support vector machines. Feature transformation is another crucial aspect of feature engineering. This involves creating new features from the existing ones by applying mathematical transformations. For example, logarithmic transformations can be useful for handling skewed distributions, while polynomial features can be generated to capture nonlinear relationships. Furthermore, domain knowledge can be leveraged to create features that are more informative. In a case study involving credit risk prediction, domain expertise might suggest creating a feature like the ratio of debt to income, which could be more predictive of default risk than the raw amount of debt or income alone. Feature selection is the process of identifying the most relevant features for the model. Reducing the number of features can help in decreasing model complexity, reducing overfitting, and improving computational efficiency. Techniques like recursive feature elimination, lasso regularization, and tree-based methods are commonly used for feature selection. RFE works by recursively removing the least important features based on the model's performance, while lasso adds a penalty to the model to shrink less important feature coefficients to zero, effectively selecting a subset of features. Tree-based methods, such as those used in random forests, provide feature importance scores that can guide the selection process. Dimensionality reduction techniques, such as principal component analysis and t-distributed stochastic neighbor embedding, are also employed in feature engineering to reduce the number of features while retaining as much information as possible. PCA projects the data into a lower dimensional space by identifying the directions that maximize variance. In a practical scenario, PCA might be used in image processing tasks to reduce the dimensionality of pixel data, thereby speeding up the training process while preserving critical information. TSNE, on the other hand, is more suited for visualizing high-dimensional data in 2 or 3 dimensions, making it easier to identify patterns and clusters. Automated feature engineering tools, such as feature tools, are gaining popularity as they can significantly speed up the feature engineering process. Feature tools uses a technique called deep feature synthesis to automatically generate new features by stacking multiple operations on top of each other. This can be particularly useful in scenarios with complex datasets, where manual feature engineering could be time-consuming and prone to human error. Real-world applications have demonstrated the power of effective feature engineering. In a study on predicting diabetes using electronic health records, feature engineering techniques such as the creation of features representing the frequency of medical visits and the calculation of average lab test results over time were crucial in improving the model's predictive accuracy. Another example is in the field of natural language processing, where feature engineering involves extracting meaningful features from text data, such as word counts, TF-IDF scores, and sentiment scores, which enhance the performance of models in tasks like sentiment analysis and document classification. The iterative nature of feature engineering means that it often involves a cycle of hypothesis generation, feature creation, and model evaluation. The feedback from model performance is used to refine the features further. This cycle is supported by frameworks such as scikit-learn in Python, which provides a robust environment for implementing and evaluating machine learning models. Experiment tracking tools like MLflow can also be integrated into this process to manage and compare different feature engineering strategies systematically. The challenges in feature engineering include dealing with high-dimensional data, ensuring the interpretability of features, and avoiding data leakage. High-dimensional data can be addressed through dimensionality reduction techniques, as previously discussed. Ensuring interpretability involves selecting features that make sense in the context of the problem and can be explained to stakeholders. Data leakage, which occurs when information from the test set leaks into the training set, can be prevented by strictly adhering to temporal order in time series data and using cross-validation techniques appropriately. In conclusion, feature engineering is a fundamental component of developing effective AI models. It requires a combination of technical skills, domain knowledge, and creativity to transform raw data into meaningful features that enhance model performance. By leveraging tools and frameworks like Pandas, feature tools, and scikit-learn, professionals can implement feature engineering techniques efficiently and effectively. The iterative nature of the process, coupled with the use of automated tools, allows for continuous improvement and adaptation to new challenges. As the field of AI continues to evolve, the importance of robust feature engineering practices will only grow, making it an essential skill for any AI implementation professional.